Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about two-stroke marine engines. So let's dive right into it. Now, before we jump into this, because this engine is kind of odd, so we have to understand what exactly is the need, because everything is built for a need. Because you cannot be like, oh, why don't we put jet engine in our cars? Again, you can do that. There is a motorbike that does that. It's just not practical. So what's the need here? Well, need comes from commercial shipping, as in like shipping containers, and these puppies are huge at this point in time. From an economics point of view, they are ludicrously big, meaning there is a lot of incentive to make a huge ship. Meaning in 1988 we started to create class C ships that was like 6,000 to 8,500. Then we went to D ships that were 15,000 containers. Then we went to E ships that were 12,500. That was in around 2014. And from basically by 2019 we have ships that can carry 25,000 ship systems. That's huge, humongous. So in this sort of scenario, there is economic demand there. That's like people are like, dude, we want more power. So what is their requirement? Because again, be mindful, there are bigger things than this. For example, aircraft carrier. So what is their requirement? What is these people will want? These people want, first thing, they want a lot of power for low cost. This is very clear. That's why you can't just put nuclear reactor in there. You can do that. It will be wise. It will be practical, even cost effective. It's just that capital would be so high that people are like, bro, I'm sorry. Me cannot do this. So that is the first point. It has to be cheap in terms of not only running cost and also in terms of capital. So it has to have a lot of power for low cost. Another aspect, continuous operation for months, meaning it cannot be like a jet engine. Jet engines are really good, but maximum a jet engine can go is like few days. You cannot expect a jet engine to run 24/7 into 365 or even a month. These puppies actually have voyages that are 1 month long or even longer than that. So they need engines that can reliably, sustainably, I'm running, and that's it. That's it. Like, you do not be like, oh, it's overheating. No, bro. Like, I'm designed to do this. I'm going to keep doing this for 1 month or even 2 months continuously. That's the aspect. And they, because of the priorities of the deal that they are doing, that they have to be very easily serviceable and maintainable, because they know, like every engineer, at least at this scale, understands that if you have an engine, if you love it, it will take care of you. If you don't love it, it will go boom. So for that reason, they have realized that maintenance have to be planned thoroughly, scheduled properly. In those sort of system, the engine has to be in such a way that it's like, yeah, I get it. We can maintain it, repair it. Cannot be like, oh, it requires like, super complex structures and like only one port in the entire world can service it. No. This has to be simple, easy to maintain and all that jazz. Ideally, even in the ship itself, if you have, let's say, multiple cylinder, one cylinder goes bad, ideally you should be able to handle that in sea itself. And again, these requirements are huge. Like, you want a lot of power for low cost, you want continuous operations, that's brutal, and you want easy serviceability and maintainability. That's a lot of demand. So what are you willing to give up in return of that demand? Well, size and weight, meaning it's big engine, nobody cares. It's heavy engine, nobody gives a damn. That's the whole benefit of this. That's why we can even have an engine that can take care of this. So we come to two-stroke diesel. Now, why exactly two-stroke and diesel? Well, diesel systems have this what we call compression ignition. What does that mean? That simply means when you have petrol system, petrol or gasoline as you call it, you go there, you squirt fuel, you have air, you compress that puppy, and you use electricity to ignite it. Basically, like spark plug goes, it goes boom. Now, why the heck you have to do that? Well, simply because compression ratios are low. If you have high enough compression ratios, you can literally have boom, just from the compression, exactly like diesel engine. So diesel engine has much higher compression ratio. Now, benefit of that is like higher the compression, the more thorough the combustion happens, the more oomph it creates, the more work you can extract out of it. So that directly translates to efficiency. Higher efficiency meaning low running cost. That's GG. Then we come to another aspect, which fuel to use? Well, they use heavy fuel oil. Now, unfortunately, there is no definitive standard about this. For example, when I say petrol is same across the planet, when I say diesel is same across the planet, when I say kerosene is same across the planet, jet propellant same across the planet. This fuel oil, they are kind of weird. They do not have exact name. So they may be called bunker oil, heavy fuel oil, marine oil, ship oil, that sort of thing. Basically, it's very heavy fuel, as in like even heavier than RP ones, as in kerosene. It's much lower than kerosene. Now, this is made as a byproduct. So byproduct, super low cost, everybody loves that. And because it has such a high density, it's really power dense, meaning how much liter of space you have to allocate for your fuel is very low. Like it's very high density, like very, very GG amounts of density. And to make sure that this puppy can sustain it, this has to be a marathon runner. It can keep on going, more going, even longer going. It runs at very low RPM, meaning 100 RPM. You're like, dude, that's low. Yeah, that's how low it is. Like, it's like, you can see it. Like, I'm not even joking. Like, if these engines are running in real time, you can put a camera there and you can look at it. It's like you can count it. That's how slow it is. You can just like, not that super fast. But benefit of that is that if you have a cylinder wall, you have a piston going like this. Here's the deal. If you have X amount of speed and he's going up and down, let's say it creates Y amount of heat. Now you're like, what if I make it 2x? The Y will not go to Y. Y will go 4y. So higher the speed, the heat you create out of friction goes exponentially high. To give you a context of that, in F1 engine, they can go very high RPM, like ludicrous RPM, 15,000 RPM. Here's the deal, why don't they go higher than that? They did. But idea was like, once you reach that point, the friction losses of doing this is so high that your engine is inherently not producing more power. So there is a peak optimum curve. So you want your things to give you a lot of oomph and last long time, reduce the RPM. For example, petrol engines can easily run up around 4,000 to 10,000 RPM, while diesel basic unturbocharged could run at 1,500 to 3,000 if diesel turbocharged, or if you are like very high turbocharged, it can go to 5,000 RPM. Again, much lower than petrol system, so it has much longer lifespan. Same goes with diesel engines, locomotive. Those can be running for weeks and they have very low RPM. This have to run for months, even lower RPM, 100 RPM. So lower the RPM, the longer the life it will have. Then how to get the oomph? This puppy are so huge, they cannot be measured in horsepower. It's really too small. So they have to be measured in megawatts. Yes, megawatts. Some of the big ones can go up to 80 megawatts. So how do you get that much oomph out of it? You do not have the RPM. How do you get the power out of it? Well, stroke length. These puppies have long stroke, meaning it travels meters, not 1 meter, meters. As in, like, it's not like, it's like very, very long stroke. Like, compared to a person, like, that's how long it is, like multiple meters long stroke. Consequence of that design is that if you have very long stroke and a lot of oomph coming out of it, because these puppy can burn 100 grams of heavy fuel oil per stroke. That's a lot. Like, the amount of energy is there in that 100 grams of fuel is like, you can move your car like a kilometer or so. And this puppy is consuming that in like one stroke. It's like, done. So it does need cylinder wall to be like robust. So consequence, the stroke length, if it's long, you cannot have the angle like this, cannot be way too long. It will become way too long to sustain that. So they have to have two systems where you have a piston rod, then you have a connecting rod. Connecting rod goes like this, and then you have the crank. So it does have one extra part compared to a system, but it is required. Otherwise, it will not have that rigidity that it needs for the cylinder to last a very long time. Everything in this is designed for long life. So, and super long stroke allows you to have gigawatts of power. Like, oomph, the oomph that this puppy creates is huge. Like 80 megawatts of shaft power. That's a lot. And there is no spark plug. There is no electrical hoo-ha that you have to deal with. And unfortunately, I wrote it wrong. It does not have air intake valve, meaning normal 4-stroke systems generally have valves. There will be air intake and there will be air exhaust. If it's a high performance system, it may even have 2 air intakes and 2 exhaust, like 2 cylinders, like whoosh and 2 whoosh. So here, there is only one. Now, why is that? Well, somebody designed a very long stroke and they put sleeves around it, meaning there is a hole there. And once the piston comes out, the air pushes the basically exhaust out there, and then there is a valve there. Jet allows the exhaust valve. That's all there is. You have one exhaust valve. The air system is completely no moving part there. Only one exhaust part. And it does require compressed air to start, because be mindful, this air system will not work unless there is enough oomph in the air. It cannot start on ambient air. It does require like 2 bars, 3 bars, depending on the design. They will tell you like how much bars it has to have, but without compressed air, this will not start. And I mean in the air, but it also needs compressed air to start to spin this puppy, because again, there is no starter motor that can rotate that. And be mindful, many of the time they are directly connected to the propeller, so there is no clutch, there is no gearbox. So these are the choices that people made. Then how the heck this puppy operates? Well, it's rather simple. It's 2-stroke, not too much complexity. You start with pressurized air at the bottom, and then the piston moves in. The air charges, rushes in. There is a lot of vents there. The air rushes in. Air goes up. Then you squirt fuel into it. The piston goes up. Piston compresses the air and fuel mixture, and it goes to what we call top dead center. And the moment it reaches top dead center, boom. it goes boom, and then piston goes down, extracting work out of it, and then exhaust valve opens, then that hot gases goes out. That hot gases goes to what we call turbocharger. Turbocharger basically spools up the turbine spools up the compressor spools up the air intake charge, meaning once you start this, you do no longer need to supply compressed air. Turbocharger will take care of it. So that's how you get it. And piston goes down, exhaust valve opens, hot gas turbocharges it, and air is now compressed. Now be mindful, compressed air are hot, so it does have a water cooling system to cool it down to 40 degrees Celsius. Be mindful, other engines may have different manual. The manual I looked into it, that said 40 degrees Celsius. The reason why they said like they do not want to cool it more, even though they could, is that there is a very chance of condensation in this location, this chamber, basically air intake. It was not desirable, so they are like 40 degrees Celsius, good enough. And then this cycle repeats. Very simple system. You just like piston goes up, fuel and compressed air and fuel goes boom, it goes down, scavenges the air system, exhaust goes to the turbine charges it up, the air intake is completely charged. It happens 100 times a second. But the stroke length is long. Like you can see that this is a person, and again, this is real scale. So it's huge. These turbines, basically piston lengths are huge, like very, very huge. So what about the auxiliary system? Well, they do have a lot of auxiliary system, meaning even though the engines are inherently simple, they require a lot of love and attention. For example, this is their exhaust valve. You will notice they have turbines. Why the heck they have turbines? Well, this is to maintain what we call even wear. For example, if you have something this huge, no matter what kind of machining you will do, there will be some tolerance error. And not to mention, exhaust products are never clean. They are erosive. So inherently, some part will be eroded more, some would be less. So how do you maintain it? You put a turbine there, turbine spins a little bit, every exhaust pulse, basically. Pulse 5 degrees, pulse 6 degrees, 7 degrees. It rotates a little bit, little by little. Consequence of that is that after continuous cycling, it's acting like a tube, is tamping out everything. Basically, wear is completely level, so seal integrity is always optimized. Surprisingly clever idea, and I'm like, and these things are huge, as in like bigger than me kind of huge. So that turbine is just there just to make sure that exhaust part lasts longer, and it does need complex air compressed air system for plumbing and starting. Now why the heck it needs compressed air for starting? Well, it needs air intake for that intake manifold, but here's the deal, how the heck you spin that puppy? You can't have a starter motor because it will be too huge. So what they do is literally from the point where they have fuel injection, they may have a different valve where it's just like opening compressed air directly, compressed air is pushing it down. So compressed air will push it down, then it will open the valve system, another system will push the basically piston down. It's acting like how a combustion process will act. It's just using compressed air to do that. So that's how they will go psh, 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 psh. They will keep doing it until it reaches 100 RPM, and then they will start injecting fuel. At that point in time, hopefully this puppy will start. So it does need very complex compressed air system. Be mindful, it needs compressed air for the air intake and compressed air to push everything down. On top of that, it also needs complex mechanism for valve timing. Basically how fuel injections are timed and valves are timed, that controls the direction, basically the RPM. Directionality, clockwise or counterclockwise. If you need reverse direction, first you stop this puppy, then you start it in reverse, and that requires another complex series of valve mechanism. So that's why like engines are rather simple, nothing too complex, but in terms of how do you run that is very complex, especially the reversing mechanism. Like other like some brands have like camshaft, they shift the camshaft and there is a different lobe that is designed for counterclock rotation. There is one lobe that is designed for clockwise running. So they can shift that. Another system is where they change the sequencing different ways, air compression system, very complex system. Then you have high pressure oil and lubrication, because even though these things are running at low RPMs, they are huge, like they're huge, multi-ton huge kind of thing. So they do require very high pressure oil, otherwise it will simply wear down. And air blower for engine starter. So these are just the auxiliary system. So what we can expect in the future? Well, these things have reached a point where they are absolutely mature. Like engines that were made in 1990s, many of them are still in service, and they are very robust kind of puppies. They are like, bro, we got this. And many times they have been serviced, upgraded, rather than just like being discarded. And not to mention, ships are also very expensive. So they do last a very long time. And what the biggest innovation that has happened compared to this 100-year-old technology is basically computer controlled fuel injection sequence for emission control. Meaning if you time it just right. You can burn the fuel so completely. Be mindful, this fuel is dirty because again, it's a very heavy fuel oil. It does have very high sulfur content, and it could create too much noise if you are not controlling the combustion processes efficiently. So it does require some serious amount of emission control, which requires very complex computer control. Then another thing which I have already covered is hybrid turbocharger. That's acting as a waste energy recovery system, because be mindful, the RPM would be 50. That's creating a lot of oomph, exhaust pressure. That exhaust pressure is driving the turbine. Turbine is driving the compressor. The compressor creates more oomph. That oomph goes into higher RPM. Okay, here's still what happens after that? It starts to waste that energy. Basically, veins will open up so it does not spool up too much. But what if you did not do that? What if instead of like, hey, waste that energy, is like, what if we extract it? So you put a motor generator unit and then now you extract that power. Benefit of that is, in this sort of large ship, it's huge amount of power. How much? Some of the system where early testings were able to extract 700 kilowatts of power. How much is that in a ship context? Well, ships generally have prime mover, the main engine, and then there is an auxiliary generator. These are a small one, and these are run all the emergency systems, lighting, electronics, and all that jazz. They don't need to turn that on. Basically, of course, it will be there. It will be a backup. It is required by law. And then we're like, okay, once this puppy starts to turn, once the engine is main RPM, this can extract so much power. It's like, how about I turn that off? Like hold the 4 edges. At the beginning, it will be there. At the end, it's like, bro, I'm done. And this also doubles up as a engine starter, meaning that it does require compressed air for starting that. It is like, I can do that. Motor generator unit is like, as a generator, it's extracting wasted energy. As a motor unit, it's starting that engine. So it's a very easy way of doing energy recovery and engine start. And they only have to add one component. Given the fact that auxiliary generator is flat out not running for 1 month, it's more than good enough for enough people are just like, dude, shut up and take my money. It saves money. It's like the easiest way to save emission is just not to burn fuel. This is like, how about we use the fuel more efficiently? Then it's a very mature technology. Be mindful. What does that mean? That simply means it's limited by other factors. For example, boats. What if we can make it even bigger? Well, we can. It just may not be viable. Why? There are not that many ports. You can only go from deep sea ports to deep sea ports. There are not that many. If you have to go to crossing through any canals, many canals are flat out not deep enough. And Suez Canal kind of showed us the whole world that it cannot even handle one ship. And be mindful, this is the first time average people kind of got used to it, like how big those things are, because most people have seen normal excavator and bulldozer. When that was directly trying to claw it, then they saw like how huge the ship is. Be like, these things are huge, because most people are not running around it, where it's like, oh, this is how huge it is. It's like, it's humongous. It's like freakishly humongous, and we can make it bigger. Engine is like, dude, the technology is sorted, settled, we can make it even bigger. And this puppy alone, it will also reduce your wasted energy. So overall, we can make it bigger. We can just add a few more cylinders and get more oomph out of it. But it does not make a practical sense from like, it's like somebody else has to buy it, somebody else has to drive it, somebody else has to park it, dock it, and all that jazz. Those things are not there yet. That's why we cannot make it even bigger. So right now, these are the main control factors, and this. So this was my presentation on huge, large, 2-stroke marine diesel engine. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.